Welcome back, everybody. Hope we had a good weekend. So we kind of hastily went over, like we mentioned, all the solutions. Does anybody have any questions on any of these ones, uh, for clarity on any of those situations? On part A, please remember that you needed to bring everything to one side because the only way the quadratic formula works is if everything is on one side and zero on the other. So you have to have it in the form ax squared plus bx plus c is equal to 0 in order for the quadratic formula to make sense. Yes.
Have doing some Alex homework.
Okay.
With the seven t, or I guess the better one is the 5t squared. Wherever the 5t squared is, I have to bring it to that side. Like Alex accepted it.
It is suitable to do it either way. The convention is to leave your leading term to be positive. So if it's on the right-hand side, it's already positive. I'm going to bring everything over that direction. If it was like this, if it was 7t equals negative 5t squared plus 1, I would definitely try and bring everything over to the left so that my leading term was positive. So I'd add 5t squared, I get 5t squared plus 7t minus 1 equals 0 because I like to have my leading coefficient be positive because that makes factoring a lot easier. But it is not required. You can like I guarantee you, if you had brought everything over to the left-hand side to solve this problem, if you had brought the 7t over, if you brought the 5t squared over here and solved it, and you have negative 5t squared plus 7t minus 1, you get the same answer. It's just Alex is going to follow the convention. If you look at their explanations, like if you get a problem wrong, you look at their explanation. They're going to follow the convention of bringing bringing things to the leading term, making the leading term positive. That's the thing they usually follow. Okay, so that is the end of unit 1, unit 0 material for exam 0. Exam 0 is on Wednesday, has about 4 to 6 pages. All free response problems. There's no multiple choice. There's no fill in the blank. That's not how I do my exams. And remember, your first attempt is just your first attempt. You get a chance to get points back on the exam redo. So even if you get a 40%, you can still get up to a 70 if you turn in the redo and get everything correct. So that's the situation. If you get below a 40, I would highly recommend that you come talk to me about your exam redo so we can figure out what went right and what went wrong and how to fix it going forward. So, but that is going to be we'll cross that bridge when we get there. Which I said to my son the other day, and he said his response was, "What bridge?" Because he doesn't like this is a turn of phrase. How do you turn a phrase? Uh, he asked me the hardest one recently. He asked me, "What's the internet?" I had to explain to him, I was like, "Well, we found that on the internet." He said, "What's the internet?" Oof. That's a tough call. That's zeros and ones moving throughout the air. In short, uh, that is a very hard situation to describe. So, anyways, we're going to start up Unit 1.1. Start up Unit 1 with section or with Unit 1.1, and that is going to be next exam's material. So we are going over new material now that is not covered on the first exam, but we need to keep chugging along. I wanted to give enough time to digest Unit 0, but we still need to keep working through it. So we start off in Unit 1. Oh, yes, go ahead.
So why on your lecture notes,
Uh-huh.
there's a 0.7 and like 0.8.
Excellent question. So 0.7, we're going to go over soon. It's not needed right now. And so in order to satisfy NSHE's vice grip on us, they call this a co-requisite class, which means it has the just-in-time remediation. So 0.7, there's less of an argument for why. I mean, we could have gone over 0.7 right now. I just wanted to wait until we got over 1.3 because that's when we'll need it. And 0.8, that won't be needed until we start talking about rational functions, which will happen in Unit 2. So no need to bog us down with more of that information right now, when it'll just cause more confusion. That's the reason why. So the coordinate system, sometimes called the Cartesian coordinate system, or other times it's called the rectangular coordinate system, because we make things from a rectangle. But a lot of people will call it the coordinate system, the Cartesian coordinate system. And that comes from the famous Cartesian from Rene Descartes. I think, yeah, Rene is spelled that way. Famous French philosopher turned mathematician, though like early mathematics and philosophy, like specifically logic philosophy, had very, very similar overlaps. So he was a philosopher, but also a mathematician. The reason why we call it the Cartesian coordinate system is after Rene Descartes, or I like to say Descartes because I'm not French. But either way, Rene Descartes was the first mathematician to formalize the connection between algebra and geometry. Before him, the idea was there was geometry, which is the study of shapes and different lines and stuff like that. And then there was algebra, which was the study of setting things equal to zero and working with algebra. Like adding and subtracting things and stuff. And he was the first person to say, well, what if we were to connect the two? And he did it by saying, well, if you have an algebraic expression, let's say, don't write this down, but x squared plus x minus 1, and you make that equal to some number y, then you could think of each x value as something, and then the corresponding y value could be made into a graph, where here we call this the x-axis, and this is the y-axis. Now, in case you didn't know this, and I like we don't really spend a lot of time talking about it, all the Cartesian coordinate system is just two number lines. Mathematicians later on in your mathematical career, I think we already wrote it at one point. We write this. That means the real numbers. And then when we talk like in mathematics, when we talk about real number, we talk about the coordinate system, we write this because all it is it's two R's, it's two number lines. All it's done is you take an one number line like this, and you take another number line, and you take this secondary number line, and you just rotate it, and boom, you've got a grid. That's all it is. That's how we create 2 dimensions. Want to create 3 dimensions? You just draw another number line going out of the page and into the page. That's what 3 dimensions is. 3 dimensions is just 3 number lines. So, and so on and so forth. Then the problem after that comes, how do we draw 4 dimensions? Well, we can't. We cannot do that. We are sadly primitive creatures that can't imagine 4 dimensions. Sadly. But either way, so that is our Cartesian grid. Each tick mark on the horizontal line is an x coordinate or an x value, and the vertical ones are all the y values. So 1,5 means, so a equals 1,5 means an x coordinate of 1 and a y coordinate of 5. In case you've never plotted a point on a graph before, or it's been a long time, if I see the point 1,5, a equals 1,5, that means that its x coordinate is 1 and its y coordinate is 5. So what we will do is, starting at the origin here, we will move 1 unit to the right to find our x coordinate of 1. And then we'll go up until we have a y coordinate of 5. That is the point A right there. So we'll plot that point. That is the point A. And B will be an x coordinate of 7 and a y coordinate of 2. And so just to show you that you can do it in either order, you can start with the y coordinate of 2 and then find an x coordinate of 7. And you get the same point as if you had gone to an x coordinate of 7 and then do your y coordinate of 2 right there. That is B. That's how we plot points. So you look at its x coordinate, its y coordinate, make sure it lines up on the grid. And I'm going to do the same. We're going to use these pictures, one of them for distance and one of them for midpoints. So I want you to replot those points, 1 comma 5 right there and 7 comma 2 right there. And then I realized that we didn't really get to talk about this very much. I need to add something onto this for 126E. But just as a note, on an XY grid or a coordinate grid or rectangular grid, there are 4 pieces to it, right? There's a top right, top left, bottom left, and bottom right. We call those the quadrants. The top one is called quadrant 1. Quadrant 2, quadrant 3, and quadrant 4. It goes in a counterclockwise orientation. Starts in the top right and then goes to the left. That's quadrant 1, quadrant 2, quadrant 3, and quadrant 4.
We're gonna read the graph too, the way it goes or not.
Quadrant 1, 2, and 3, and 4. It has its uses everywhere. So it's very important to know that actually, that which one's which quadrant, especially if you plan anything in 127. One of the things that you'll be talking about a lot is where a sine curve and a cosine curve are positive, or a tangent curve, and there's a very, very strong correlation between the quadrant and whether or not a trigonometric function is positive or negative. So we're gonna like that is going to be useful knowledge, knowing which quadrant it's in. For us, not so much, but we will still mention it from time to time. If you are on an axis, you are not in a quadrant. The quadrant is everything excluding the lines. So if I have a point right here on the y-axis, that is neither in quadrant 1 or quadrant 2. It's just a point on the y-axis. But either way. So we are more interested in this course in how to use a coordinate system to figure things out. And the 2 main things we're going to discuss right now are the distance and the midpoint formulas. So the motivating example here is to determine the linear distance between the point A and B, and also to find the midpoint. So let's just say like this is a real life situation. Maybe your friend, you've imposed a coordinate system where maybe this is a home base, this is school. And then based on where your school is located, this is where you are, and this is where your friend is. And you need to get to them in the shortest distance possible. You're pulling a Ferris Bueller and you're trying to go through all the houses, go into people's backyards in order to figure out how to get to them the fastest. Like, of course, if you're trying to take surface streets, maybe you'll have to go down and then left and then maybe up and then like that or whatever. But if we were to truly be able to jump over houses and get there in the shortest path possible, that's what we're interested in, this distance, which I'm going to call D. So if these 2 points were on the same horizontal line or same vertical line, right? I can calculate that distance pretty quickly because they're on the same line, so I can just add them up, right? If I'm trying to find the distance between 1 comma 2, so an x coordinate of 1 and y coordinate of 2, and 7 comma 2, I just need to add it. 1, 2, 3, 4, 5, 6. Done. And the same thing's true here. I would just need to add it up and it would be 3. But that's not what we've got. We're on 2 different levels. We're on 2 different horizontal lines. And 2 different vertical lines for that matter. So how do we find that distance? And so what we can do is we can draw a right triangle. Like that. How is that going to help us? We'll get to that in just a moment. We said that this distance was 6. By we said, I'm saying the royal we. I said, but we all said it was a distance of 6. The royal we, my favorite. When it comes to looking at our finances, my wife and I, we looked at our finances when really she just did. She's the financial guru. I sit there and make sure I have all the documents ready for her to look at. She's way better than I am. So, that's a distance of 6. But there's another way to think about it. And this is a very useful thing to understand in mathematics. From here to here. That's a distance of 7, right? And this is a distance of 1. So what is this purple distance? 6. And how do we get that? We did 7 minus 1. We snipped away 1. Like, imagine that black line there is a piece of string or a piece of wood that's 7 inches long or 7 feet long. And I snip off 1 foot of wood. There's that'd be 7 minus 1, which is 6 feet left over. So I'm going to write that down. That's going to be 7 minus 1, which is 6. And by a similar argument, yes, this is 3, but it's really 5 minus 2, which equals 3. You have a piece of wood measuring all the way up to 5, and then you're snipping off this 2 feet. You're taking away 2 feet to get a total amount of 3 feet. And why am I mentioning that? Well, the purple is the difference in the x coordinates, and the green, even though it's kind of hard to see this green, the green is the difference in the y coordinates. That'll play a role in a second. But now that we have that, we now have a triangle with both legs known, the vertical leg and the horizontal leg, and the hypotenuse, which, in case you don't remember what that is, the hypotenuse is the longest side of any right triangle. So the reason we've done this is now we can use the Pythagorean theorem, if you guys remember what that is. If you don't, by Pythagorean theorem, which, by the way, the Pythagorean theorem says that for a right triangle, leg squared equals hypotenuse squared. You've probably seen it as a squared plus b squared equals c squared, but I want to make sure that when you use the Pythagorean theorem, it's the leg squared plus the other leg squared equals the hypotenuse squared. In the Pythagorean theorem, c, if you're going to be writing it algebraically as a squared plus b squared equals c squared, you have to know that c is always the hypotenuse. The hypotenuse is the one by itself, always, in the Pythagorean theorem. So by the Pythagorean theorem, since we're dealing with a right triangle, it's going to be that leg squared, so 3 squared, plus the other leg squared, so 6 squared, is equal to the hypotenuse, which we just called d. So d squared. Any questions on anything we've done so far? Yeah, HYP for hypotenuse. Thank you. I should have mentioned that was using abbreviation. You can write if you know how the Pythagorean theorem works, you can write a squared plus b squared equals c squared. It's just I want to make sure we understand. Pythagorean theorem only is leg squared plus leg squared equals hypotenuse squared. The hypotenuse always needs to be by itself in the theorem. And the proof of that, if you'd like to see it, I'm happy to show you at some point. There's many cool proofs like that I can show you. We can also look up online. It's a very, very useful theorem. There's been many different proofs over the years, but they proved that way back in the time of the Greeks with the Greek mathematician Pythagoras. But anyways, 3 squared is 9, 6 squared is 36. So we've got 45 equals d squared. And in order to solve for d, we can take the square root of both sides, But remember, if you do that, you have to add the plus or the minus. When thinking about it from a mathematical standpoint, if we are just looking at the formula, like not formula, but the equation 45 equals d squared, mathematically that has two solutions. That has the positive square root of 45 and the negative square root of 45. But we are looking at this in a very, very specific lens. We are looking at this in the concept of distance. And there's no such thing as negative distance. We can't go backwards. Like we can't have a drawer measure, like, or a house measuring negative 25 feet by negative 30 feet. It doesn't make any sense. So we can circle this one and say, or highlight the minus sign and say, ignore since distance must be positive. So that gives us the final answer that d is equal to the square root of 45, which is approximately, if you plug it into your calculator, 6.71. That's the distance. And so if you were able to actually impose a coordinate system on your hometown, and that's where you and your friend live, A and B respectively, you can find out that the distance between you guys is exactly 6.71 miles, or is exactly the square root of 45, or approximately 6.71 miles away from each other. Now the question is, that's the first question, is how to find distance. And we just did it for this specific problem. Now the thing is trying to find the midpoint. So if I were to draw these two connected by a line segment, right there, and if I'm doing a rough estimation, I'd say it's roughly about there. That's the midpoint M. Midpoint M. Now, once again, so I'm gonna erase this real quick, or I'm gonna move it away for just a moment. Actually, no, I'm gonna erase it. Delete. If they were on the same line, here and here, it would not be too hard to find the midpoint because they're all on the same line. So they have the same y coordinate, like the same y coordinate. So what we would really need to do is just find out where this is. But that's the average of the two values. That's the average of the two things. Whenever you're given a list of data values, if you want to find the average, you add them all together and divide by the total number of things. That's how you find the mean average. So if I was to take, if I added up all of your guys' exam 1 score or exam 0 scores and then divided by the total number of students, that would give me the mean average score on the exam. And I guarantee you, if you take 8 plus 2 and divide it by 2, that's 10 divided by 2, and that's 5. So, and the same thing would be true if this was like this instead. We'd take 7 and add 4 to it and get 11. And the midpoint would be 11 divided by 2, which is 5.5. So, the midpoint, if you were to draw these lines again, want this one. There we go. This right here will be the average of the y coordinates. That is, the y coordinates are 5 plus 2 divided by 2, which is 3.5. So the y coordinate of this thing is 3.5. The y coordinate of the midpoint is 3.5. You take the average of the two y coordinates, 5 and 2, you get 3.5. And the same thing goes for the x coordinate right there. That's the average of the x coordinates. 7 plus 1 divided by 2, that's 4. So our midpoint must be therefore M is equal to our X coordinate first. It's always X comma Y. So 4 comma 3.5. It's always X comma Y in our system. We always do X then Y. Sure, in some alternate reality, we do Y comma X, but that's not the way we do it here. So we were able to find the midpoint and the distance in this one specific example. That's great and all, but how do I find the distance if I now find out that Johnny moves to another place in town, maybe closer, maybe further away? How do I find out how to find him? I don't want to have to find out, like, I don't want to have to define the wheel every single time, impose a new coordinate system, plot the 2 points, make a triangle. There's got to be another way to do it. And there is. There's a formula. So let X sub 1, Y sub 1. So those are subscripts. You could make, like, some books say A comma B and C comma D, but the convention is to make them subscripts. So these are 2 unique points. So we'll plot them on a graphing grid. So let's put X sub 1 here and Y sub 1 here. Yeah, don't draw this line. I mean, like, just draw it your best that you can. So, and then also plot X sub 2, Y sub 2. So we'll do X sub 2 over here on the left side of the X-axis, and then maybe Y sub 2 is there. So this is the point X sub 1 comma Y sub 1, and this is the point X sub 2 comma Y sub 2. That. Should have used red. Change that to being red. Okay, and then here's the vertical one. Like that. So these are 2 arbitrary points in space. I'm just saying X sub 1, Y sub 1 is in quadrant 1, and X sub 2, comma Y sub 2 is in quadrant 3. It could be that both of them are in quadrant 1. It could be that one of them is, like, the first one's in quadrant 2 and the second one's in quadrant 4. It really doesn't matter at the end of the day. As long as I have 2 points, I can always create a line connecting them to create a hypotenuse, and then draw a vertical line and a horizontal line to create a right triangle. Here, the purple distance will be X sub 2 minus X sub 1. Oh, I meant to make that. Sorry, this is X sub 2, Y sub 2, and this is X sub 1, Y sub 1. I'm sorry about that. It just makes it make a lot more sense. X sub 2, comma Y sub 2. It's X sub 1, comma Y sub 1. So sorry about that. Sorry. But the purple length is going to be X sub 2, the further right, minus the further left. And then similarly, this distance is Y sub 2 minus Y sub 1. Now we're dealing with it in arbitrary terms. So it's the exact same argument. You do the upper coordinate minus the lower coordinate. That's just what we did before. When we were finding distance, we found the distance, like the differences between the X coordinates and the Y coordinates. And then to find the averages, should be like the average would be right about there. That's the midpoint. And this is the distance D. This is going to be x sub 1 plus x sub 2 divided by 2, or sorry, y sub 1. And this will be x sub 1 plus x sub 2 divided by 2. The averages of the x coordinates and the averages of the y coordinates. That gives you the midpoint. So we have the two formulas in question. Now that we, I mean, this is a pretty ugly looking chart of all this stuff being written, but it's meant to show you that like the way this is proven, the way that we find these formulas is by posing a triangle and dealing with averages. So the distance formula, which you'll be provided on the on exam 1, says that the distance D is equal to the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. And the midpoint formula, capital M, is equal to the coordinate point x sub 1 plus x sub 2 divided by 2, comma y sub 1 plus y sub 2 divided by 2. Those are the formulas. In all their glory. Beautiful formulas. Beautiful formulas. Now, why did I talk about Pythagorean theorem? This doesn't look like the Pythagorean theorem. Except it is. You don't need to write this down. Just write out what you've written. But if I square both sides, I get that d squared is equal to x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. That's where the formula comes from. By the Pythagorean theorem, the purple leg squared, which is x sub 2 minus x sub 1 squared, plus the green leg squared, which is y sub 2 minus y sub 1, so y sub 2 minus y sub 1 squared, is equal to the hypotenuse squared, which is d. But I don't want to find d squared when I'm finding distance. I don't want to find the distance squared. I want to find the distance. So what do? I take the square root of both sides, and then don't worry about the plus or minus because the minus version doesn't really count for distance. That's where the formula comes from. It's the Pythagorean theorem. And then the midpoint is coming from averages, from probability and statistics. So that's the way the formulas come to be. Now, once again, you will be provided those formulas. Please don't make the mistake that many students make. They think they're a hero and they can just say, oh, I got it memorized. And then they forget that this one's a minus, whereas this one's a plus. It's a big difference. It kills me whenever a student or like they've got the exact right formula, except they put the like for the midpoint, they do x sub 1 minus x sub 2. That throws it all off. That's wrong. And it breaks my heart. So please don't make that mistake. Instead, know that the distance is the difference between the two x coordinates and the two y coordinates both squared, and the midpoint is the averages of them. So that's why you have to add in that case. Any questions on those formulas? If not, we can now plot them and find the different distances. I want you to write the answers as, I don't think we've talked about it yet, about the difference between exact and approximate. Exact answers are without any decimal, without any decimal expansions. So, or a finite decimal. So for example, 0.5 is an acceptable exact form because it's a finite decimal. But as soon as it's 511111111 like that on forever, that's no longer, I mean, if you write the dot dot dots, now it's exact. But if you write if you approximate it to like that, that's an approximation. So square root 5 is an exact value. 2.1 whatever it is, 2.5 or whatever it is for the square root of 5. That's an approximation. So I want it in both forms, as we'll see in a second. But right now I want you to plot those 2 points. A is -2, -1, and B is 6, 5. So for A, that's an x coordinate of -2 followed by a y coordinate of -1. It's right there. and B, an x coordinate of 6 and a y coordinate of 5. So the formulas are, and I'm going to write them down again for this one. You don't have to have them memorized, but an easy way to memorize things is to rewrite them down every single time you have to use them. We talked about that with the quadratic formula. If you want to memorize the quadratic formula, just rewrite it every single time. X equals negative b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. And so the distance formula, leave a little bit of space and then write the distance formula like this. So like leave a little bit of space underneath a and b, the points there. But d is equal to the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. So the formula is as written. Which one's my x sub 1, y sub 1, and which one's my x sub 2, y sub 2? It doesn't matter. The formula was in generic terms. It just so happened that x sub 1, y sub 1 was here and x sub 2, y sub 2 was here. But it really didn't matter. You could have made this x sub 2, y sub 2 and this x sub 1, y sub 1. It doesn't matter. And they could be in any quadrant they want to be in. So as long as you're consistent, it does not matter. Convention would state that the first point should be x sub 1, y sub 1, which is what we're going to do. And the second point is x sub 2, y sub 2. But there's no problem in swapping it. If you're bored this weekend, don't do it right now while you're studying for the exam, but maybe after the exam date, maybe mess around with it, check it out. Great bonding experience with your family, with your mom and dad. Like just go through and check this problem out. Try it in reverse. Try making this first one your x sub 2, y sub 2, and this one your x sub 1, y sub 1. I guarantee you will get the same answer for both the midpoint and the distance formula. But convention is to make the first one your first point and the second one your second point. So in this formula, that would be the square root of x sub 2, which is 6, minus x sub 1, so minus negative 2, which you could rewrite as x plus 2, which is what I'd recommend that you do. But either way, plus y sub 2, which is 5 minus negative 1, or plus 1, which is what I'd prefer you get to the point of doing. That's the square root of 8 squared plus 6 squared, which equals the square root of 100, which equals 10. So this is this is one of the cases where the exact form and the approximate form are the exact same thing. But if that was the square root of 99, then we would have a little bit of a problem. Any questions on that? And the midpoint formula, so I'll write it for this one, but then in the future, I'm not going to, but I encourage you to do so if you want to have a quick way to memorize these facts. Just rewriting the formula each time will really help. The midpoint was x sub 1 plus x sub 2 over 2, comma, y sub 1 plus y sub 2 over 2. Average of the x coordinates, comma, average of the y coordinates. So x sub 1 was negative 2 and x sub 2 is 6. This is equal to negative 2 plus 6 divided by 2, comma, negative 1 plus 5 divided by 2. That's going to be 4 divided by 2, which is 2, and then 4 divided by 2, 2. Any questions on that? All right. We're going to do E to C together, and then I'll let you guys do E, or B, excuse me. Let's plot those points. So E is -3 comma 0. That's an X coordinate of -3 and a Y coordinate of 0. That's on the X axis. That's right here. That's E. And F was 5 comma 0. It's an X coordinate of 5 and a Y coordinate of 0. That's also on the X axis. So this one, you could just do it by adding them up. The distance is 1, 2, 3, 4, 5, 6, 7, 8. The distance will be 8, but let's verify it with the formula instead. So here's our x sub 1, y sub 1, and x sub 2, y sub 2, though it doesn't matter. If you want to channel your inner Bob Ross and decide to do it flipped around, be my guest. But the formula is that it's d is equal to the square root of the difference of the x coordinates. So x sub 2, which is 5, minus x sub 1, minus -3 squared, plus y sub 2, which is 0, minus y sub 1, which is also 0 squared. And lo and behold, that will equal 8, which is the exact form and the approximate form because it's just a nice number 8. The midpoint, you already can you can probably tell that the y coordinate of the midpoint will be 0 because they're on the same line. The only thing that's going to be different is where their middle is in terms of x. But the formula works regardless. So m will equal x sub 1, so -3 plus x sub 2, which is 5, divided by 2, comma, 0 plus 0 divided by 2. Y sub 1 is 0, y sub 2 is 0. 0 plus 0 divided by 2, that's 0 again. So this becomes 1 comma 0, which is exactly where you'd get it if you were to plot it. Like if you were to try and find the halfway point between those two x coordinates. Any questions on that? The formula works for any 2 points. So in particular, it will work for part B, which I'd like you guys to go ahead and start working on. Small note though, I would really, really, really like you guys to get to the point where if it's a minus, that you immediately move it to plus and understand the connection that they're the same thing. Because minus is the same thing as adding the positive version, right? So if it were me writing this, like if I was a student in this class and I was writing this, I would instead write this -6 plus 2 and 5 plus 1 instead. I'd like you to get to that point. It's useful to understand that connection. But in the meantime, I'd like you to do B. I'm going to slowly fill in details. I also want you to plot the 2 points. All right. If you're still working through it, continue to do so. But if you finish, check your work. I'll pause the recording so that I'm not sitting here waiting for a second. So to talk through it now, once again, you can just label them x sub 1, y sub 1, and x sub 2, y sub 2, though it does not matter which one you choose to be your first one. So long as they're consistent. One of them needs to be an x sub 1, y sub 1, and one of them needs to be an x sub 2, y sub 2. Always as an x comma y. So 2 minus 5, that's -3, but you're squaring it, so it becomes +9. And then -4 minus 5, that's -9, but you're squaring it, so it becomes +81. 9 plus 81 is 90. So the distance is the square root of 90. That's the exact form. And the approximate form, if we're rounding to 2 decimal places, which was what was requested, would be 9.49-ish. The midpoint, yes, it's got fractions in it. So it's 5 plus 2, your x plus 1, x sub 1 plus x sub 2. That's 7/2, which you can't reduce any further. You could write it as 3.5, and that's still technically correct as an exact form, but I don't like to do that because then it just like that 2 is a very nice case, because whenever you divide by 2, it will always end up being 0.5 or nothing. It'll either divide it nicely or leave it with a 0.5. And that's just unique about 2. And then 5 plus -4, that's going to be 1, divided by 2, that's 1/2. So the midpoint of these two numbers is 7/2, 1/2. The reason why I like to have the graphing paper there is that you can then check your work and see to make sure that 7/2, which is 3.5, 1, 2, 3, that right there, that ends up looking exactly like the midpoint right there. And so you can kind of verify it. You can make sure that it doesn't make any, like, it makes a lot of sense. All right. Okay, fun problems to think about. Suppose the midpoint between 2 points, A and B, is 3, -2. If A is -7, 1, then determine the distance between A and B. Okay. We'll do this one and then we'll take our break. The distance between A and B would be x sub 2 minus x sub 1, like we need to use the distance formula, but we don't have B's coordinates. There's actually 2 ways to solve this. So I'm going to split this problem down the middle and give us both options. I'll show the other option unless someone figures it out first. How would you guys go about doing this? What would you do? So whenever you're tasked with a problem in mathematics where you don't know where to go, ask yourself, what should I do, or what do I know? So it says determine the distance. Well, I know the distance formula, and if this was on the exam, the distance formula is provided. It's on the back page. So I know the distance formula, but in order to use the distance formula, I need to know my 2 points. I know what A is, but I don't know what B is. How will I ever survive? So let's just call B. So this is option 1. Find B, which we're going to rewrite as x sub 2, y sub 2, and then calculate distance. Have A. A is equal to -1 comma 7. That's my x sub 1, y sub 1. What piece of information have I not used? The midpoint. I haven't used that information at all yet. There must be some reason that was given to me. There's got to be something I can do with that. The midpoint is x sub 1 plus x sub 2 divided by 2, comma, y sub 1 plus y sub 2 divided by 2. I know what x sub 1 is. X sub 1 is -1. X sub 2 is unknown. And then y sub 1 is 7 plus y sub 2 divided by 2. But the midpoint is 3 comma -2. So we have that 3 comma -2 is equal to -1 plus x sub 2 divided by 2, comma 7 plus y sub 2 divided by 2. And the only way that that could be true is if the x coordinates were equal and the y coordinates were equal. So this tells me that 3 is equal to -1 plus x sub 2 divided by 2, and -2 is equal to 7 plus y sub 2 divided by 2. We'd solve that like we do anything. And this is why we needed to talk about fractions. This is why we did 1.3 before we started talking about this stuff. How do I solve that linear equation? As soon as I see fractions, I say I want to get rid of them. So I'll multiply both sides by the LCD. In this case, the LCD is 2, because that's the only fraction that's present. So I'll multiply both sides by 2 to cancel it on the right-hand side. And I get 6 is equal to -1 plus x sub 2, which tells me that x sub 2 is equal to 7. Any questions so far?
How'd you get 7?
I added 1 to both sides to get the x sub 2 by itself. By a similar argument, I multiply both sides of the equation for the second one, the y sub 2 equation, multiply both sides by 2, subtract the 7. I get that y sub 2 equals 11, -11, that is. So B is the point 7 comma -11. Any questions so far? Now we have point B, we have A, we have the distance formula. We can find out what it is. So D is equal to the square root of x sub 2, so -7 minus x sub 1, so +1 squared, plus -11 minus 7 squared. That's equal to the square root of 388, which is approximately 19.70. Once again, it's 7 plus 1 because it was 7 minus -1 for our x sub 2 minus x sub 1. And then, so that's 8 squared plus 18 squared. That'll add up to 388, which is approximately 19.70. Yes. In the distance formula? Yeah, it's supposed to be an 11. Any other questions? Okay. So let's take our first break. We'll come back at 12:05, and I'm going to give you the other option during the break, and I'm going to put it up on the screen. We're back. And so I have this secondary option. You can take a picture if you'd like. We're gonna move on. But the thing is, another way to do this problem, which I hadn't thought about until I sat down with another class, and I was like, you know what, there's another way. if we know where A is and we know where where M is, the midpoint, that's half the distance from A to B because the midpoint is halfway between A and B. So if we find the distance between A and M and double it, that would give us the full distance, right? Like visually, what's happening, you don't need to draw it. Like here's A, here's B, and then M is somewhere right about there. And this distance is the same as this distance. So if I find the distance from A to M and double it, I get the distance from A to B, as you see here. I found the distance D from A to M, so oh damn, right there. And then sorry, press the center button. And then notice the difference, it goes from AM and now it's AB. So it's the distance from A to B now, and that's 2 times that same number. They don't look the same at first, but I guarantee you if you plug in your calculator 2 square root 97, or if you try and plug in square root 388, your calculator will automatically simplify this radical, and it will be 2 square root 97. True story. All right. The next one. So like feel free to take a picture of this if you haven't already written it down. I'm going to move on, or we can you can take a picture after class or during the break, the second break. The next one. The vertices of a rectangle are positioned at -3, 0, 0, -3, 1, 4, and 4, 1. Let's plot all those points. -3 is 0. That has an x coordinate of -3 and a y coordinate of 0. That's right there. 0, -3, that's an x coordinate of 0 and a y coordinate of -3. So that's the point right there. 1, 4, that's an x coordinate of 1 and a y coordinate of 4. That's right there. And then 4, 1, x coordinate of 4, y coordinate of 1, right there. Okay. So the way to figure out the distance, the area of a square equals length times width. But we don't have those, and unfortunately, this rectangle has not been put flat. So finding the distance, like the length and the width, results in a kind of a difficult situation. So we'll call this one the length. It doesn't matter which one you call the length and width, but I'm going to call that one the length and this one the width. The length is going to be the distance formula. Which is the distance from -3, 0 to 1, 4. L is the distance between those two things. And so that would be, in this case, this is my x sub 1, y sub 1, and this is my x sub 2, y sub 2. But once again, it does not matter which one comes first. You could have just as easily made 1, 4 your x sub 1, y sub 1 instead. But either way, if you do that, you should get the square root of x sub 2. So 1 minus -3, so 1 plus 3 squared, plus 4 minus 0 squared. And that'll equal the square root of 32. Any questions on that? Find the length. This is a very useful application of the distance formula. Well, I mean, very useful. I mean, in the grand scheme of things, you're not going to really see this, right? This isn't going to happen unless you're like dying, like you're falling into a ravine in the water and I come to save you. as the water's filling up in the car, I'm going to be like, what's the distance formula? Come on, come on. And then you're panicking as the water's filling up, it's like, can't open it up until you gotta, what's the next part? What's the next part? Come on, come on. Oh, you're dead. So that's a situation where it would be useful, but otherwise not really super useful. But in these specific niche cases where you need to be able to impose a coordinate system, that's how this works. Global positioning, it's all based on coordination and coordinate system. Granted, we're using spherical geometry there a little bit because the Earth is circular, is spherical, but all global positioning systems is based upon mathematics and making distance between two places. So, anyways, I'm gonna save the other one, W equals, and I want you to figure it out. The area, the final answer is 24 meters squared, or units squared. So I know we're assuming the unit of measurement is meters. That is the answer. I'd like you guys to verify that on your own time. Not today, not tomorrow, but after the exam, yes. No, you're going to use the distance formula again because the midpoint would find a point. We're interested in finding a distance. But it should give you 24 meters squared. All right. Any questions on that? Cool problem, though. Fun problem. Whenever you encounter a problem in mathematics and you don't know what to do, best thing you should do is say, what do I know? And then start jotting things down. Like this question is asking us to find the area of a rectangle. What's the area of a rectangle? It's length times width. I write that down. If this is a 10-point problem, that's worth 1 point to me. That's some partial credit. Knowing what the formula is, that's what you're supposed to be doing. It's for encouragement. If you start writing those things down, you'll be surprised at what your mind can come up with. It can start making random connections, and hopefully it makes the right one. But either way, you won't get any connections unless you write something down. And be okay with using your eraser. It's totally fine to use it. It has a purpose. So yeah, that's that one. And then we will move on to the next portion. That is the coordinate system. Those are the two things. Now we get to where Rene Descartes got his point. This is why we call it the Cartesian coordinate system. So recall that a solution, we had the concept of a solution for a one variable equation, but the concept of a solution can be generalized to inputting multiple variables. So the solution to a two variable equation is an ordered pair. It's two variables that we can, just in case we wanted to, we can impose our own order on it, x then y. So a solution to a two variable equation is an ordered pair that forms a true statement when plugged into the equation. So for example, x squared minus y squared equals 4. The ordered pairs -2, 0 and square root 20, 4 are solutions where 5, 3 is not. Checking -2, 0, we're going to plug in -2 for x, 0 for y. And what do you get? -2 squared is +4 minus 0 squared, that's 0. 4 minus 0 is 4. We get a true statement. Try square root 20, 4. All right. Square root 20 quantity squared minus 4 quantity squared. Does that equal 4? Yes, it does. Because you get 20 minus 16, that's 4, and that equals 4. Whereas 5, 3 does not solve it. 5 squared minus 3 squared, does that equal 4? And it's going to give you 16, which does not equal 4. So I usually put a little circle with an X through it, saying that's not true. So the observation that Rene Descartes had was saying, well, if these are ordered pairs, if this is a variable, if this is two variables, then I can think of each one as a slot on a number line and then connect them with a graph by creating this coordinate point. So each ordered pair from that's a solution is a point on a coordinate point on a coordinate grid. So in fact, the solutions of an equation create the corresponding graph. The solutions to an equation create the graph. And actually, technically speaking, vice versa, though going backwards is a lot harder. Being given a graph and trying to figure out what the equation of the graph is, that is a far harder endeavor unless we're given some specific parameters. If we know the curve given is a circle, it makes it that narrows it down and that makes it possible to find. If we know that it's a quadratic, we have processes that can make it easier to find those equations. But by and large, if I give you the graph of some unknown equation, finding the equation that works is very difficult. But the point being, the solutions of an equation create the corresponding graph. And as such, we can find solutions to an equation and use them to create the graph. So, well, how do I find these solutions? So you can you've probably heard it before. Have you heard the terminology independent and dependent variables? Independent means it doesn't matter, like that one it doesn't depend upon anything. So X is usually considered the independent variable and Y is the dependent variable because it depends upon what X is. And so the great thing about an independent variable is whenever I plug in a specific X value, I can find the corresponding Y value that solves it. So for example, the line Y equals 3/2 X minus 1 is represented by this curve in space. And all the points on this, you can verify it for yourself that you can plug in X equals 2 and you'll see that your Y value ends up being 2. You can plug in 4 for X and you'll see that your Y value is 5. You can even go crazy. You can do X equals 3 and you'll find that you get Y equals 3.5. Or you could even go even more crazy and go 3.1 and find the corresponding Y value as well. You can keep finding as many points as you want. Almost every curve every equation in existence usually has infinitely many solutions, every two-dimensional equation. So just as an aside, just to see what I'm saying, if X is equal to 4 and Y is equal to 5, we got 5. Does that equal 3/2 times 4 minus 1? Yes, it does. 3/2 times 4, that's 6. Minus 1, that's 5. So 5 equals 5, and so on. So every single point on that curve works. So that is the first way we learned how to graph things. When we were baby mathematicians, when Rene came along, in order to graph these things, he would make charts. He'd be given an equation like this one, find several solutions, find several solutions by picking an X value and finding the corresponding Y values. That's terrible handwriting there. I'm going to rewrite values. We can pick X to be whatever we want and then find the corresponding Y. Or it could potentially be Y values. It could be multiple depending on the equation. In this case, it's only going to be one, but in certain cases, you might get multiple. So the convention is usually to pick about 4 to 5 points. I'm going to pick 5. And I'm going to do them pretty close together. I'm going to do -2 to +2. So I'm going to choose x equals -2, -1, 0, 1, and 2. So if I plug in -2 for x, then y equals -2 squared minus 3. That's going to equal 1. So we have the corresponding point that solved the equation, -2, 1. When we plugged in x equals negative, when we plugged into a -2 for x, you could solve for y. Y is already solved for, so there's no need to like take square roots or bring anything over. But either way, you get y equals 1. So we have the point -2, 1. We can plot that on the graphing grid. So -2, 1, that's right there. Plug in 1, a -1 that is, you get y equals -1 squared minus 3. That's -2. So we have the point -1, -2. And we'll plot that point. An x coordinate of -1 and a y coordinate of -2 to plot right there. Then we'll do 0. You get -3. So you get the point 0, -3. Right there. And then if you plug in 1 or 2, you should get -2 and then 1. So we have the points 1, -2 and the point 2, 1. Like that. Now I can continue on with this. I could plug in x equals -3 and x equals +3 and -4 and then +4 and then -5 and +5. But that seems like it's going to be a lot of work. But the shape is kind of making itself known. It's going to make a U shape. So it's going to end up looking like this. It doesn't need to be perfect, but that's what it will look like. Lo and behold, that is a quadratic, which we'll talk about in 1.6. This is the quadratic curve y equals x squared that's been shifted down 3 units. But this is how we started off in Rene Descartes' day. We didn't know as much as we know now. So in order to figure out what graphs looked like, they just had to plot them by plugging in random points. And then they started noticing some behaviors of certain types of graphs. Specifically, they started noticing things about quadratics and other polynomials, and that's where Unit 2 comes into play. But that's how we can graph a polynomial or graph a function or an equation, in fact. It doesn't necessarily need to be a function, but we can graph an equation by just picking a random x value and finding the corresponding y value or values. You could do it in reverse too. You could start with a y value and then find corresponding x values. It doesn't work as nicely in this case, but it can be done. Just as long as you just make up a random choice of x or y and then find the corresponding y or x, the opposite variable. All right. So that's how we create a graph. And now we can talk about the other properties of them. So the first thing that we are very interested with in mathematics, and there's a reason for that, are intercepts. Given the graph of a curve, an x-intercept is a point a comma 0 where the graph intersects the x-axis. If it's a point a comma 0 that has an x coordinate of a and a y coordinate of 0, it's going to be on the x-axis. Hence, that's where it goes through it. So a graph has a graph of a curve has an x-intercept if it crosses through the x-axis. Similarly, a y-intercept is a point 0 comma b where the graph intersects the y-axis. All right. So a frustrating thing for me about Alex and people at large, an x-intercept or a y-intercept is a point. It is a coordinate point, and as such, it has an x and a y coordinate. However, because of the context, if you say it's an x-intercept, we already know it's on the x-axis, and therefore we already know that the y-coordinate is 0. So many times you will see people say that the x-intercept is 4. That is not 100% correct. If you said that the x-coordinate, the x-intercept is at x equals 4, that is more correct than saying the x-intercept is 4. But this is the gray area. So in Alex, they'll probably make you just write the value. So they'll like if the answer is that the x-intercept is 4 comma 0, they probably will just make you write 4. It's not technically correct, but it's correct enough. If you accidentally write it as a coordinate point and it marks it as incorrect, please email me and I will give you full credit back. That's a confusing thing. I like to write them as coordinate points. But Alex and a couple other programs would like you to write just the x value or the y value. Since it can be assumed that one of them will be 0 if you're talking about an x or a y coordinate, a y intercept. So just let that know. I will probably be very, very clear on exams if I want it as a coordinate point. I'll say like listed as a coordinate point or not. So given the graphs of the curves below, determine the x and the y intercepts. So the x-intercept or intercepts are where it crosses the x-axis. So I'm going to color code this in red. And there's only one spot where it crosses the x-axis, right there at 6, negative 6. So negative 6 comma 0 or x equals or negative 6. Some people will just accept the answer being negative 6. I like it to be the coordinate point because that's what it is. And I find that helps us a little bit more in terms of understanding graph theory. The x-intercept was negative, the x-coordinate was negative 6, the y-coordinate was 0. And the y-intercept, well, this one only has 1 right here. So that's going to be an x-coordinate of 0 and a y-coordinate of 1, or just 1. I'm going to erase the parentheses. I would prefer the coordinate point, but I think Alex prefers the number aspect. Any questions on that? Okay. Is it? Okay, cool. We're doing good on timing. Good, we're caught up. Right. The x-intercepts. For this next one, I'd like you guys to find them yourselves. Also look on the details. I'm gonna zoom in so people. And once again, if you forgot to print off the notes, or if you have no way of printing off the notes, let me know, and we can work something out. See what we can do. I have the answers up here if you'd like to check your work. If you're still working on it, continue to do so. Pause the recording for just a second. All right. We've taken a little breather to see it. So the x-intercepts, that's where it crosses the x-axis, which I've done in red, though it is hard to see. Like just looking at the x-axis. So there are 4 spots where it crosses the x-axis, or intersects it. It touches the x-axis. That would be at -6, -2, 0, and 4. So the x-intercepts are -6, 0, -2, 0, 0, 0, and 4, 0. And by a similar argument, same thing is true with the y-intercepts, but it's where it crosses that vertical axis. That's -7, -3, 0, 1, and 5. So 0 is 0, 0. The origin is a spot that is both an x-intercept and a y-intercept. It's the only one that is both. But anyways, that's how we find the x-intercepts graphically. Are there any questions on that? No? Okay, that's all fine and dandy, right? If I'm given a graph, that's fun points. Those are like, oh yeah, that's it. But how do I find it algebraically? How do I find it algebraically? The key when you're at an intercept, one of the variables, or one of the coordinates, let me say that, one of the coordinates is 0. So I'm going to show you a procedure, but I'd rather you memorize the one thing and instead extrapolate instead of trying to memorize 2 different things. An intercept, what you noticed about the previous situation, every single time an intercept always had one coordinate that was not 0 and a 0. So for an x-intercept, it was always an x value and then 0, always. What the x value was was varying, but the y coordinate was always 0, and vice versa for the y-intercepts. The x coordinate is always 0. So we can use that to our advantage. If we know we're looking for x-intercepts, we automatically know that the y coordinate will be 0. That just has to happen because it's an x-intercept. So if we want to find the x-intercepts, we're going to set y equal to 0 and solve for x. And for y-intercepts, we're going to set x equal to 0 and solve for y. Because once again, an x-intercept requires that the y-coordinate be 0. That's the only way you get on the x-axis, is if your y-coordinate is 0. And so you can set y equal to 0 and solve the remaining stuff for x using any methods that we've learned, and vice versa for the y-intercept. So in practice, if you want to find an intercept, set the opposite variable equal to 0 and solve for your desired intercept. If you're trying to find an x-intercept, set y equal to 0 and solve for x. If you're trying to find a y-intercept, set x equal to 0, the opposite variable equal to 0. So, for example, unless there's any questions on that. 13x minus y over 2 minus 15 equals 0. We want to find the x-intercepts or intercept and y-intercept or intercepts. So for the x-intercept, we're going to set y equal to 0. And what will that do? Well, 13x will stick around, but I'm plugging in 0 for y. So it's minus 0 over 2 minus 15 equals 0. That gives me 13x minus 15 is equal to 0. Because remember, 0 divided by any non-zero number is 0. 0 divided by 2 is 0. 0 divided by -10 is 0. 0 divided by 0 is indeterminate, but which we've talked about before. Any questions so far? And so we've got, excuse me, sorry. We've gotten very, very good at solving these guys since we worked with polynomial equations. The answer is x equals 15 thirds, 15 thirteenths. So the intercept is is 15 thirteenths comma 0. Or 15 thirds. 13ths, sorry. Looks like a B. I wrote 15 thirds there as well. I don't know why I wrote that. The y-intercept. We're going to set x equal to 0. So for the y-intercept, we're going to set x equal to 0 and see what happens. We get 0 minus y over 2 minus 15 is equal to 0. So we got negative y over 2 minus 15 is equal to 0, which gives us y equals negative 30. So we got 0 comma negative 30 or just negative 30, depending on the context. And I want you to see where that came from. How did I get y equals negative 30? Try and do it in your head with verifying it in your head without using a calculator or without doing any algebra. I want you to get to that point in your mathematical skills. With your arithmetic, you should be able to do that by the end of this semester. Ideally, by Wednesday for the exam. In short, add 15 to both sides. You got negative y over 2 is equal to 15, and you'll multiply both sides by negative 2 to cancel out the dividing by 2 and cancel out the negative, and that's where you get y equals negative 30. Any questions on that? Okay. I'd like you guys to do part B. Try it yourself. See what you get. Here's the x-intercept. And here's the y-intercept and all the work showing for it. So x-intercept. Whenever you're finding an intercept, you're always setting the opposite variable equal to 0 and solving for your desired intercept. So with an x-intercept, you're setting the opposite variable, y, equal to 0. Because when you're on an x-intercept, your y-coordinate will be 0. You just know that, so you can plug it in and solve what the x value will be. So we get x squared plus 3x minus 0. So you can just immediately ignore it if you'd like, and get x squared plus 3x equals 10. I subtract the 10 from both sides because that's a polynomial equation. X squared plus 3x equals 10. That's a polynomial equation. And how do we solve those? We use the zero product rule, i.e. you want to set everything on one side and 0 on the other, and then rewrite it as a product. So x plus 5 times x minus 2 equals 0. That's the numbers I found at the bottom. I needed to find two numbers that multiplied to negative 10 and added to 3, which ended up being 5 and negative 2. And then I set each factor equal to 0 using the zero product rule or zero factor rule. And you get x is equal to 5 or 2, which means that the intercepts are negative 5 comma 0 and 2 comma 0 if you want to write them as coordinate points. Or if you're looking at it on ALEKS, they usually just want you to write the x coordinate, the x value, so negative 5 comma 2. Similarly for the y-intercept, you're going to set the opposite variable, in this case x, equal to 0. X squared, so 0 squared, 0. 3 times 0, that's 0. So it's 0 plus 0 minus y equals 10, or really just negative y equals 10. Divide both sides by negative 1, and you've got y equals negative 10, or the better way to write it, in my opinion, which is as a coordinate point, every y-intercept has an x coordinate of 0, and then comma negative 10. Any questions on that? Okay. Now this one we're going to omit because we did not go over how to solve absolute values. And we don't really have the time to do so. Sad as that may be. I love talking about absolute values, but they are their own. If this course had an extra credit, sure, I'd talk about it, but I don't have enough time. So We're going to omit that one. I decided against it. And we'll just go to this last one. All right. What are the x-intercepts? There are none. And same thing with the y-intercepts. This graph does not cross the x or the y-axis. So there's none. That can happen. A graph can have 100 x-intercepts and no y-intercepts. It can have a million. Oh, sorry, 1 second. You're filling in the email you have. So that might be the best. Like they'll be that's what we got. Service down there. Yeah. Of course. All right. So it is possible to have infinitely many x-intercepts and no y-intercepts, or vice versa, or some random combination. It all depends on the problem. All right. And that covers unit 1.1. Do we have any questions on that? Main things, distance and midpoint formula and intercepts and how to find them. All right, let's take our next break. We'll come back at 12:55. 12:56, actually, 12:56. All right. And then we'll start up 1.2. People watching the recording, go do some squats or some guided meditation. I don't care. All right, we're back. And we're going to start up circles, but actually not really going to start up circles, because in order to talk about the circle, we need to talk about the square, not an actual square, but completing the square. Okay, this is a process, but it is a very commonplace process that will happen over and over again. If you plan on taking Math 181, you probably have to do it. If you take 127, you might have to complete the, no, you will. If you plan on taking Math 127, you will have to complete the square. If you plan on taking 181, you might have to do the completing the square. If you take 182, you will definitely need to complete the square. If you take anything after that, there may be a situation where you have to do it. This happens all the time. And there's good things in it. This is a very, very good algebra exercise. Like, you know, like the leg press is like a perfect thing for leg day, right? Because it works all the different leg muscles. So like, especially if you add on the thing where you push you curl your toe forward or whatever, like works every single part of the leg. It's a great exercise. This is a great exercise for your mathematical abilities. So sometimes in mathematics, it's useful to change quadratic expressions, right? Ax squared plus bx plus c from their standard form, which was ax squared plus bx plus c, to their vertex form, which is a times the quantity x minus h squared plus k. This process is called completing the square. So I've got an example of it. If you want to go from standard form to vertex form, you complete the square. And if you want to go from vertex form to standard form, you simplify. By foiling. If you want to go from vertex form, all you need to do is do x minus 3 squared, foil that out, distribute it in the 3 after that point, combine, again, simplify, and you will get back to the same thing. I guarantee you, you can show that these things are equal. You can prove it to yourself by actually simplifying it, or you can plug in several different values and you'll see you get the exact same number. So, one thing of note, that a value is the exact same a value. That is a feature, not a that is like when that's a feature, not a fluke. The a that's listed on the standard form and this a here, they're the same number. That's a nice little nifty trick. Because once we get to 2.1, we'll find a way to complete the square quickly. But it requires a little more nuance, and so a lot of students just stick with this method to do things. So, okay, completing the square. There's two cases. the case where your leading coefficient is 1, and the case where your leading coefficient is not equal to 1. The case where it's equal to 1 is very, very nice, in my opinion. Step 1, identify the B term. And calculate B divided by 2 quantity squared. And I'm going to tell you this. So when you are in this section, when we start talking about circles in a little bit, they will show you how to complete the square in a different way. The difference, though, is that their way requires you to have an equation. My method does not. And my method's better for actually working out your body better, your brain. It's working out your brain muscle better. So yes, their method, if you look at it, their method looks simpler. But it's because they're dealing with it when it's just an equation. Whereas my method deals with it when it's an expression as well, which is far more useful. So even though if you're looking at the explanations on Alex when you get it wrong, they will do it a different way. You're more than welcome to do it that way. I'm just going to do it my way for this course because this way is more applicable to any situation. So in this situation, we've got x squared plus 10x minus 8. This is your b term. B is equal to 10, positive 10. So I'm also going to calculate b over 2 quantity squared. So b divided by 2 squared is 10 divided by 2 squared, which is 5 squared, which is 25. Ideally, though, you should try to do this in your head or on your calculator without writing it down. Because you don't have to. It doesn't hurt, but it's not necessary. So identify your b term and then calculate b divided by 2 squared. 10 divided by 2 is 5, squared is 25. Now that you've done that, step 2, add and subtract b divided by 2 squared after the bx term. This will make a perfect square trinomial. In the example. Add, subtract b over 2 squared after the bx term. Add and subtract in that order in particular. And I can explain why in a little bit. So we've got our original thing. It's x squared. Right, are people still writing? Yeah, I'll wait. We have x squared plus 10x minus 8. So after the bx term, the middle term, the 10x, I'm going to add and subtract b over 2 squared, which in this case was 25. So I'm going to do this. X squared plus 10x plus 25 minus 25 minus 8. I don't believe we've talked about this yet. We talked about cleverly multiplying by 1, right? You can multiply by 3 and it doesn't change anything because multiplying by 1 doesn't do anything because 1 is the multiplicative identity. 0 is the additive identity. And there's a thing called that I like to call cleverly adding 0. This right here is cleverly adding 0. Because if I immediately add 25 and then I immediately subtract it, that's adding 0, and adding 0 doesn't do anything. In the grand scheme of things, it makes it still equal. X plus 0 is just x. X squared plus 10x minus 8 is the same thing as x squared plus 10x minus 8 plus 0. So I can add 0 whenever I want, and that's okay, but I'm going to do it in a very, very clever way. I'm going to add 25 and then immediately subtract it. Doing so gives me a perfect square trinomial every time. These first three terms, this is x plus 5 squared. Now you could figure that out by factoring it, like find two numbers that multiply to 25 and add to 10, you'll find that it's 5 and 5. And then you can factor it like that. However, there is a way around that. There's a way that that's pretty cool. There is a fact of the matter is the number that's there in orange, the plus 5, that is always b divided by 2. But anyways, we'll get to that in just a moment. So whenever you add and subtract this 0, when you do it that way, when you've done the correct b over 2 squared and added and subtracted, the first three terms will always form a perfect square trinomial that factors nicely. And so at the end of the day, this is going to equal x plus 5 quantity squared minus 33. And so the thing I'm going to mention the symbol that's here, it's always b divided by 2. So in our situation, b divided by 2 was 10 divided by 2. It was 5. So plus 5. If it was, just to do an example here in just a moment, let's say it was x squared plus or minus 18x plus 199, like that. B divided by 2 is negative 18 divided by 2 is negative 9. If you complete the square on this one, it will be x minus 9 squared plus something here. It will be every single time. The number portion in the perfect square trinomial, it's always b divided by 2. Negative 18 divided by 2. So in this one, this example that's coming up in just a moment, it's going to become x plus 7 halves quantity squared. Because half of 7 is 7 halves. It doesn't go nicely into it, or 3.5 if you want to. Any questions on that process? There's a lot going on here. Several things. Number one is that now we have a new thing that we can do, which is cleverly adding 0. Mathematicians use it all the time. The proof of the product rule in calculus hinges upon cleverly adding 0. A lot of upper division theorems, they get proved by using by cleverly adding 0. It happens all the time. It's surprising how often it's used. It's another tool in your mathematical toolkit. Not nearly as useful as multiplying by 1, so it's not like your hammer or your screwdriver. It's more like a level, right? We use a level frequently in our toolkit just to make sure things look nice. So it is there. It has uses, not as many as cleverly multiplying by 1, but still plenty of uses. Let's do another example. So this one, leading term is 1. So we are in case 1. So step 1. The b value is 7. So b divided by 2 squared is 7 divided by 2 quantity squared, which is 49/4. I know it's weird, by the way, and if we have time, I can explain why this process works and what we're trying to do. In fact, maybe I can. Maybe we can do that if we have a second. So that's our b term. B is 7. B over 2 is 7 halves. That's going to be useful later on. And then the number that we're going to add and subtract is 49/4, right after the bx term. So step 2, You've got x squared plus 7x. We're going to add 49 fourths and then immediately subtract 49 fourths to cleverly add 0, and then minus 18. And so I can immediately write the answer. The first three things, that will automatically become x plus 7 halves. I guarantee you, if you x plus 7 halves squared, I guarantee you, if you try and FOIL it or do whatever you want to do to factor it, you will get x plus 7 halves quantity squared. And then this will simplify to minus, use your calculator for this, 121 fourths. Any questions on that? Just use your calculator to do negative 49 fourths minus 18. You'll get negative 8. You'll get negative 121 fourths. Okay? Don't waste precious brain space on that. Instead, remember the JG Wentworth 877 cash now. It's an important thing to memorize. They drilled that into our heads. They did it.
So it's back here. First section, and then you like.
Simplifying the other section. Yes. So, like, you know what? We can do a little tiny proof of it. We like just to show you the reason why something is true. So, we want it to go from x squared plus bx plus c to x minus, let's just call it capital D, x plus d squared plus k, right? That's what we want it to get to. Well, what do I notice about this? When I FOIL this out, I get x squared plus 2dx plus d squared plus k. So, if I want to find out what d is, that means that b, there's only one thing that has an x on it. It's this stuff. So in order for this to actually work out, it means that 2 capital D is equal to B. So to find out what D is, which is what we're trying to do, we just divide both sides by 2. Our D value is B divided by 2. And then to figure out what C is, that's when you use the other stuff here. But the point is, that's the reason why we're choosing B divided by 2, is that if you were to FOIL this out with this, whatever this number may be, it's going to give you 2 times that number, and that 2 times that number needs to be equal to the original B. So that's why the capital D in this case is B divided by 2. That's how it comes to be. Comes to exist, comes to be, the letter B. Anyways, that is something you don't need to memorize that, but that is the reason for it. And now we can move on to case 2. Case 2 is, what if the A value is not 1? So an example, 3x squared minus 24x plus 5. This is something that is very common in math. Is if it's not nice, make it nice. Step 1 is to factor out the A coefficient from just first and second terms. A lot of times mathematicians, if they get something complicated, they say, well, what if it wasn't complicated? Let's just stop that right now. I'm not gonna deal with that. I'm gonna work on something smaller. I don't want to. And so this is what we do. We're gonna factor out the A coefficient from just the first and second terms. You can factor it out from the third term sometimes, but rarely that number is divisible by it. And furthermore, it just makes it give you more fractions. It's unnecessary. So in this example, we're going to take our 3x squared minus 24x plus 5, and we're going to factor out the 3 from the first two things. X squared minus 8x plus 5. Now, the question you may be asking is like, well, how did you know to do that? I'm telling you now. This is something that mathematicians struggled with for a long time to try and figure out what would work. There is a method that looks similar to the previous method, but instead of being b over 2 squared, it's going to be b over 2a quantity squared. And that's fine and it works, but I don't want you to have to memorize a bunch of different techniques. I'd rather you practice the algebra that's going on here. This is good algebra practice. It's talking about how to factor, not just how to factor a nice thing, how to factor out a mini GCF, which is something that's useful to do. And then we're going to be talking about cleverly adding 0 and working with a lot more algebra. This is a good process to practice algebra skills. So now that we've done that, this is what I was saying by what do mathematicians do when we're tasked with something that's complex like this, where the coefficient isn't 1? We say, well, what if it was 1? And what we do is we factor it out. And now, if you look on the inside, like if I take this, and instead of looking at, I just zoom in on just that, that is a quadratic with leading coefficient 1. So I can complete the square on the inside of the parentheses by doing what we did in case 1. And that's what step 2 is. Complete the square on the inside like in case 1. Like case 1. And I hope it's like when I write INEX, it's saying in this example. That's what I mean by in X, in the example. So that's the step procedure in general, but in this specific example, this is what's going to happen. Bless you. Good progress. And you guys are superstars. You've been doing this for over 2 hours now. You're doing great. Keep it up. We got a few more weeks. Then you don't have to sit through 3 hours of lecture a day. Try to make it breaking up, but it's just the nature of the beast. So in this example, we've got 3 times the quantity x squared minus 8x and parentheses plus 5. This is something I'm writing in purple. This is something I'm typically doing in my head, but I want us to see it in paper, on paper. So our b term is -8. So b divided by 2 quantity squared is -4 squared, which is 16. B divided by 2 is -8 divided by 2. That's -4. -4 squared is +16. So on the inside of the parentheses, I'm going to cleverly add 0 and complete the square on the inside. So this becomes 3 times parentheses x squared minus 8x. I'm going to cleverly add 0. So I'm going to add 16 and then just immediately subtract 16 on the inside of the parentheses. And don't forget about your +5 that you were working on. The whole point of doing this, the whole point of adding that b squared over 2, b over 2 squared, is that now the first 3 terms of your inside, that makes a perfect square trinomial. It makes this x minus 4 quantity squared. It's always x plus your b term. Your b term is your b over 2. Your b over 2 was -4. That's why it's x minus 4. If b over 2 was 5, it would be plus 5. If b over 2 was -13 thirds, you're at x minus 13 thirds, so on and so forth. So we've got this. 3 bracket parenthesis x minus 4 quantity squared minus 16 end bracket plus 5. We said no, I'm not going to work with a harder case. I'm just going to look at it like it's a simpler case and work like that. Mathematicians love to do this. We love to say, like, I don't want to deal with those big numbers. Let's just factor it. Let's just factor it out and see what happens. That's actually how we prove the quadratic formula. Oh, I didn't get to show it with this class, but I did get to show it to my other class. They wanted to see the proof of the quadratic formula, so I ended up proving it for them. And I wrote it down. You don't need to know the proof, but if we have a second, we'll show it. Because it's cool. So, any questions on any of the algebra so far? It's a lot of algebra. It's a lot of algebra going on. So please ask a question if you haven't. No, just stretch it. Gotcha. Totally fine. Step 3. The last step is to distribute and simplify. To complete the square. To finish it off. In the example, once again, we have 3 bracket parenthesis x minus 4 squared minus 16 end bracket and then plus our 5. So I'm going to distribute the 3 in. I can't bring the 3 on the inside of the parentheses because it's not squared as well, but I can put it right out front like that, and then I can distribute it into the 16 as well. So it becomes 3 times the quantity x minus 4 squared minus 48 plus 5, because 3 times 16 is 48. And then we can combine the negative 48 and the plus 5 to get our final answer, which will be 3 times the quantity x minus 4 squared minus 43. And that is the completed square. Well, I told you that, guys, there was a bop for the quadratic formula. There's a headbanger, as the kids say, on the quadratic formula. We'll end class a little early so we can listen to that. And like, yeah, you can leave early if you don't want to listen to the song, but like, why would you want to miss listening to like we're talking like T Swift level musical taste right there, or Kendrick Lamar if that's like if you're more into rap or whatever. Like I'm not too big on the rap scene. I don't know who the big names are. Or and Terra if you're into the metal scene. Or Limp Bizkit if you're into the new metal scene, right? You guys remember Limp Bizkit? Do you know they came out with another album? Crazy. If you haven't listened to Limp Bizkit, I don't encourage it, but you can if you want to. Okay. I'm getting sidetracked. So this one, negative 2x squared plus 12x minus 5. We're going to work through the process again. The fact of the matter is the leading coefficient is not 1. So we say, well, I don't want to deal with that. I want to make it 1. So we will factor out your a value, your a coefficient, which in this case is negative 2. So step 1, I'm going to factor out a negative 2 from the first 2 terms. That makes it a positive x squared minus 6x, and then minus 5. Like that. Then I'm going to complete the square on the inside of the parentheses. So that negative 2 Your B term here, I'm going to kind of do this off on side note land. B is -6, so B divided by 2 squared is -3 squared, which is 9. We're going to complete the square on the inside, which means we need to find the B over 2. We identify the B coefficient. So that's -6 in this case. Divide by 2 squared. So -3 squared, that's 9. So we're going to complete the square on the inside of the parentheses. So it becomes x squared minus 6x plus 9 minus 9. We're going to cleverly add 0, then minus the 5. And the whole point of that is that now the first 3 terms have created the perfect square trinomial. It is x plus or minus what? Very, very close. -3. It's always going to be divided by 2, and that's just by the design. Always by the design. So that's going to be x -3 quantity squared. So what we really have is we have -2 bracket parenthesis x minus 3 squared minus 9 end bracket minus 5. This is by no means an easy thing. There's a lot of steps going on here, but it all hinges upon so with this, if you want to become a stronger mathematician, try and memorize the original process when the case is equal to 1. And then if you can memorize that the non-1 case is just the first step of the non-1 case, which is factoring out the a, so you do get into case 1, you can let your brain finish the rest and get comfortable with more algebra. So this one, so -2 times the quantity x minus 3 squared minus 9, all in brackets, and then minus 5. Now step 3 is all about distribution. We're going to take this -2 and we're going to distribute it into both sets on the inside of the parentheses. We've got -2 times the parentheses x minus 3 squared plus 18 minus 5, which gets us our final answer, which is -2 times the quantity x minus 3 squared plus 13. I've got an extra example right down below, 4x squared minus 8x minus 17. Maybe we'll do that on, not on Wednesday, but on Monday of next week, once we come back. So that we can understand, we can get a refresher on this process, because we're going to be focusing right now on studying for the exam. Move from there. Any questions on that? Because if not, then we go on to actually talking about what this section is about. So this was kind of like a side detour to talk about a very, very common process. Once again, for one more reiteration, if you're looking at the explanations on ALEKS on when they talk about completing the square, they will do it differently than I do it, because they will be doing it with the assumption that you're dealing with an equation. I'm going to do it in the case where you have an expression, so no equal sign. How do you work with it there is very, very similar but different. And it gives you more practice of algebra. But if you like their method, you can go ahead and do that. Just know that when we move forward, when we start talking about quadratic functions in unit 2.1 and how to complete the score with them, we'll be doing a different method. We'll be doing mine. So instead of learning 2 different methods, might as well struggle through this one and learn it now. All right. So circles. We've all seen them. We all know what they look like, of course. But how do we define them mathematically? So the mathematical definition of a circle is that a circle is the set, it's the collection of all the points that are equidistant from a fixed point called the center of the circle. That fixed distance from the center to any point on the curve is called the radius. radius. So in picture format, I've got a circle, and then you'll notice that I drew the center as an open circle, and that's important. The center of the circle is not actually part of the circle. The circle is all the points that are equidistant from that center, but the center itself is not actually part of the circle. It's just there for reference. So the center is right there. Oh, it's blue. That's the center. This is the radius r. And then I'm going to call the x coordinate of this point, I'm going to call it h, and the y coordinate k. So the center is the point h comma k. That's just a convention. H comma k is a convention. You could have just as easily used A and B to call the center, but for whatever reason, mathematicians decided on H and K. And so we'll add that note. The center is for reference. But not actually part of the circle. The center is for the reference. It's to tell you how to create the circle. And fun fact, that's actually how circles were made back in the old day. You'd put a stake into the ground, like if we didn't have paper, you put a stake into the ground and tie a string to it of the desired length that you'd want, and you just rotate it around the stake. So like you'd have stake in the ground and you tie a little string to it, and then you'd move it around in a circle to create the actual circle because it's a fixed distance around that little pivot point. So that's what it is pictorially. And that's how we used to view it before Rene Descartes. Before Rene Descartes' time, before the Cartesian coordinate system, we just had circles and they were just this thing. And we learned a lot of stuff about it. There's some fascinating things that the Greeks figured out about circles and how you can use them to find different things using nothing but a compass. Not like a cool tracking compass for going on little hunts and stuff, but like a mathematical compass. Do you guys remember those things, right? It looked like this. And had a little attachment for you could put a pencil and you could like pivot. You guys remember those things? I grew up thinking that I was going to be using that all the time. I've never used it ever since. So, but they're very cool. They're very fun. What happened to compasses, man? But algebraically, once Rene Descartes got into the picture and we started realizing there was a connection between shapes and algebra, we actually were able to get that there was a thing called standard form. And standard form of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared, with center h comma k and radius so that is the standard form of a circle. And then there is another format for it called general form. Which is x squared plus y squared plus ax plus by plus c is equal to 0, like that. So if you want to go to general form, all you need to do is just FOIL everything out, simplify it, and bring it all to one side. General form doesn't have very many uses. It has a few and far between, but standard form is the gold standard, hence the name standard form. Because there's so much you can see from just looking at that equation. When I look at the standard form in a circle, I know exactly what it looks like immediately, which is pretty cool. I can just draw a circle from memory by looking at it in standard form. So let's go ahead and work on graphing them. So given the following circle equations, identify the center and the radius, and then sketch the graph of the circle. Okay, so here's the thing. What's the center? I'm going to give 4 different options. 3, 2, -3, -2, 3, -2, or -3, +2. 1, 2, 3, or 4. The 2 ones, I'm assuming we can probably reason our way through and say it shouldn't be 3 or 4. It's either got to be 1 or 2. Format is x minus h squared. Is it already in a minus format? Yes, it is. It's already as x minus something. So the h value is immediately 3, and the k value is 2. In order to be, this is x minus h squared, y minus k squared, and this is r squared. So h and k, h is equal to 3, k is equal to 2. So the center is h comma k, which is 3 comma 2. And the radius, r squared is equal to 25, which means that r is equal to plus or minus 5, but we're going to ignore the bottom one. We're going to ignore the negative version because radii are positive. You can't have a negative radius. I mean, you can in a weird way when it comes to polar coordinates, which is something you'll talk about in Math 127. There are cases where that works, but like in the context we are given, we're talking about real life circles. Circles have positive radii. So yes, to solve r squared equals 25, you take the square root of both sides, which would give you the plus or minus, but we're going to ignore the negative case because we're dealing with a intrinsically positive idea. Radii are positive. So the radius is 5. Not 25, it's 5. Because the formula is equals r squared, equals the radius squared. Okay. So if we're going to graph this one, and this is the last thing we'll do, and then I would love to actually explain to you why the formula is the way it is. The way to graph a circle is to first and foremost plot the center. If on the ALEKS software, that's what they're going to do. They're going to make you plot the center first. So I'm going to plot that in blue, in purple, because that's not part of my curve. 3, 2 is right there. That's 3, 2. Then what I'm going to do now on ALEKS, once you've plotted the circle, you can move your it'll start making the circle, and the further you move out from your center, it'll start making the circle bigger and bigger. So when it comes to doing on ALEKS, you only need to just move yourself out 5 units. Like trace your pen, your mouse cursor to go 5 units out, and then it'll automatically fill it in for us. We're doing it by hand, our caveman hands, so we're gonna have to go out 5 in this direction. 1, 2, 3, right there. And I'm gonna do that in every direction, north, south, east, and west. 1, 2, 3, 4, 5 to there. 1, 2, 3, 4, 5 to there. And 1, 2, 3, 4, 5 to there. And I'll plot 3 points that are on my circle. Right there, right there, right there, and right there. And then I have to connect them with a circle as best as I can, but I can draw perfect circles, so that very, very good at drawing perfect circles, so you're impressed. And that's how you draw it. So you go 5 unit, like you take the radius and go out the east, west, north, and south directions, and you're good to go. But on Alex, once again, what will happen is imagine, so you got your little mouse cursor, right? And so once you plot this point, once you've plotted your center like that, then it'll start giving you an ever-changing circle like that. And then when you move your cursor over, oh no. When you move your cursor, come on. You get the point. Damn it. When I move it over here, it will start making the circle bigger. Like when I move it to there, it will be that big. And so all I need to do is just move it out 5 units to the right, or 5 units to the left, or 5 units up, or 5 units down, and it'll take care of the rest for me. Okay? Now, one thing you might be curious about is how does the formula come to be? Why is that the formula for the standard form of a circle? Well, it comes from the distance formula. It comes from the distance formula. The circle is the collection of all the points x comma y. This point right here. So let me make a new little side note so you can see it in action. You got this circle with centered right here at h comma k. And we want all the points so that this r is fixed at any given point x comma y. Right? So that's an arbitrary point that has to have its radius be fixed. By the distance formula, if this is my x sub 2, y sub 2, and this is my x sub 1, y sub 1, then I know that x sub 2, that the distance is equal to the square root of x sub 2 minus x sub 1. So that would be x minus h quantity squared plus y minus k quantity squared. And the distance is r. Square both sides, and you get to this formula. Square both sides of this formula right here. The square root goes away, r becomes squared, and boom, you have the formula. That's how it comes to be. It's algebra. That's all it is. But if you'd like to know more about it, please feel free to talk to me. I'm happy to show you before, after class, in my office hours, whatever it may be. But yeah, that's where we'll leave it for today. So once again, your exam on Wednesday. So student asked during the break, the exam is 1 hour and 20 minutes long in class. It's in here. As soon as you get your exam, you have 1 hour and 20 minutes. That's to stay consistent with the fact that regular Math 126 exams are 1 hour and 20 minutes. So our final exam is 1 hour and 20 minutes. As soon as you finish the exam, you are free to leave. So you could be out within you have at minimum about 2 hour, 1 hour and 30 minutes at your disposal after the exam is done. So don't worry about getting here exactly on time. If you're a few minutes late, I'll just keep a record of it and tell you when your exam time ends. And so that'll do it for today. In the meantime, I'm going to bust out the song if you want to stick around for it. Otherwise, I'll see you guys on Wednesday for the exam.